I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists. Naming something that...
So, hi, I'm Erin Redwing. I'm going to be talking today about the astrobiology of our solar system. And the reason why I'm specifically talking about the solar system is because I'm biased. I'm a solar system scientist. And so I personally think it's the coolest place to look for life in space, but that's why I'm focusing on that. So just to start, what is astrobiology? From the name alone, you can probably deduce that it has something to do with life in space. But practically, there end up being a lot of different ways that we can study or think about astrobiology, depending on what it is that we're interested in figuring out. Astrobiology as a formal scientific field is relatively new. The field in science emerged with the space program back in the 1960s. But I think it's important to note that astrobiology really has its roots in creative and philosophical thought. You know, the question of whether or not we're alone in the universe is one that's been thrown around by philosophers and artists and even theologians for centuries before scientists started to investigate this question from a materialist and empirical perspective. And I think it's important to recognize that, you know, the way we even go about trying to answer this question scientifically is based on assumptions about how we define life or what it means to be alive, as well as our preconceived notions of what universal laws are, or universal truths are, many of which are really difficult to investigate scientifically. And in science, you know, we're taught that nothing is special, that if something's not repeatable or reproducible, then it's not science. And yet, in all of the searching that we've done in our vast universe, we only have one data point to work with for studying life, and that's Earth. So in order to even wrap our heads around the idea of studying life in space scientifically, we need to be careful about the ways that we define our research questions and the scope of our study. Otherwise, it's really easy to get bogged down by all of the what ifs and all of the unknowns. So one of the ways that we can narrow our scope in order to carefully define our scientific questions is to look at all of the life that we know exists so far and figure out some common denominators. So what, at the most basic level, is needed for life as we know it to exist? There are a few things that come up, but the most important and the most constraining is liquid water. So why liquid? Well, we think that it needs to be liquid so that things can dissolve in it. This facilitates chemical reactions that are necessary for life. It's difficult to have these kinds of chemical reactions at the speed that we need for life in dry, arid environments. And why water? Well, water is a really unique molecule. It's known as the universal solvent because so many things dissolve in it. And we really don't know of any life that doesn't use liquid water in some form. We know of life that uses very, very little, but there's nothing as far as we know that doesn't use any at all. And so from this, we can start to narrow our scope from the search for life in the universe, which is a question that has many assumptions, many caveats, and many, many unknowns involved, to the search for liquid water in the universe, which has, you know, more clear materialist physical constraints. So in reframing the search for life to the search for liquid water, the idea of a habitable zone emerged. And this is basically just the radius around a star that's neither too hot nor too cold for liquid water, but just the right temperature for liquid water on the surface of a planet. And so a lot of people call this the Goldilocks zone because it's that just right, not too hot, not too cold for liquid water and for the temperatures that would allow for that. So for our solar system, Earth is right there comfortably in the habitable zone. Mercury and Venus are just a little bit too close to the sun. They're a little bit too hot for liquid water. And then Mars is just on the outer edge. So let's look at Mars. We've done a lot of exploration of Mars over the past few decades, as you can see from all this. We've had orbiters, we've landed on Mars, we have robotic rovers that are roaming around on the surface. And so what have they found in terms of liquid water and in terms of life? Well, we think we have found some liquid water, although this topic has been highly debated over the decades of Mars exploration. This is an image of a water ice glacier on Mars. It's estimated that there's likely to be some liquid water below the ice, but that water is probably quite salty, and there probably isn't a lot of it. However, we have pretty good evidence that ancient Mars used to be much more habitable. This is an image of Mars' surface where you can clearly see what looks like a river delta that's dried up. So we think that ancient Mars used to be much warmer and much wetter, and that over the past few billion years or so, pretty much all of the water has dried up, although there is still some, certainly in the form of ice. And so for all of the exploration that we've done on Mars over the last few decades, we've had no luck finding life, and we've had not even that much luck finding potentially habitable environments. Okay, so is that it then? Is the talk over? Venus is way too hot. We haven't really had very much luck with Mars. So what else is there? Well, we may have to be a little bit more creative about how and where we're searching for liquid water. So as I said before, the habitable zone is defined as the radius around the sun where liquid water can exist on the surface of a planet due to heating from the sun. But the sun's not the only form of heat in our solar system. So on Earth, for example, we also have internal heating coming from the core of our planet. And there are entire ecosystems on Earth that live at hydrothermal vents at the bottom of the ocean, completely removed from the light from the sun. And so rather than just limiting ourselves to looking for liquid water that's liquid because it's heated by the sun, let's also look at internally heated bodies in our solar system. And there happen to be a lot of those. Many moons in the outer solar system have internal heating that's due to the force exerted on them by their host planet. So I'm going to give a brief explanation of how this works. So think about the Earth and the moon. They both pull on each other. This is why we have tides in the ocean. They're due to the gravitational force of the moon pulling on the Earth, and the Earth also pulls on the moon. So now imagine that you're a moon of a giant planet like Jupiter that has a gravitational pull that's much higher than Earth's gravitational pull. So this is an image of Jupiter, Earth, and Earth's moon all to scale. So as you can imagine, that's a lot of force on the moons of Jupiter. And this force ends up dissipating in the form of internal heating. And so as a result, many of the moons of the large planets in the outer solar system have really strong internal heat sources. So this is Jupiter with its 4 largest moons, which are known as the Galilean Moons because they were discovered by Galileo in 1610. They're all internally heated due to the extreme gravitational pull of Jupiter. And for comparison, these moons are about the size of our moon. But as you can see, they don't really look like our moon. The surfaces look quite different. So let's take a closer look at one of the moons. We're going to look at Europa to start. So this is an image of Europa. You can see that it has a really dramatic surface. It's got this bright white ice with a bunch of red cracks all over. And this image of Europa was taken by the Galileo spacecraft, which was a mission that investigated the moons of Jupiter throughout the 1990s. And when Galileo flew by Europa, scientists were really surprised at the way Europa looked. And they actually found that this bright white ice is almost 100% water ice. And so that's interesting to start. But then what are all these red cracks that are all over the surface? So imagine that you have a moon with a frozen water surface and a really strong internal heat source. So a hot core and an icy water surface. At some depth into the surface, the temperature is going to be hot enough to melt the ice. And so at that depth, you're going to get some liquid water. And so what scientists found is that the cracks on Europa's surface were actually just weak points in Europa's relatively thin ice crust. So basically, the ice shell is just kind of slipping and sloshing around on top of a global subsurface layer of water. The image on the right is an image of cracks on a frozen lake on Earth. So imagine this as being basically a global phenomenon on Europa. So Europa is basically an ocean world with a crust of ice on top. And this subsurface ocean on Europa is really remarkable. It's estimated that there's more liquid water under Europa's icy surface than there is water of any kind on Earth. Okay, so that's great. We got a lot of water there, but the liquid water is covered by a layer of ice. So how are we going to get to it, or how can we even learn any more about it? Well, sometimes the cracks on Europa open up wide enough that the material from the ocean actually comes through. So you can kind of think of this like an ice volcano. So if you think about volcanoes on Earth, you've got solid rock, and then you have liquid rock or magma that erupts, and that spews out when it erupts. So for Europa, we've got solid ice, and then we have liquid water, it's kind of the magma, and that occasionally spews out in plumes and then falls down to the surface. So this is kind of a diagram of what we think Europa looks like. So we've got an icy surface with cracks that occasionally open up enough that we can have some eruption of the water underneath, and that brings up material from the subsurface liquid water ocean. And then all of that is heated by hydrothermal vents at the bottom of the ocean. So I think that sounds pretty dynamic and pretty interesting. And Europa is not the only one. There are several moons that we know have subsurface liquid water oceans, and there are even more that we think might have subsurface oceans. We just don't know enough yet. And so since these discoveries, there's been a lot of really interesting speculation about what kind of life could exist below the surface on Europa or other moons in the outer solar system, and how we could go about investigating or finding that life. So the Jupiter Icy Moons Explorer, or JUICE, is a mission from the European Space Agency that's set to launch in 2022. And the objectives of this mission are to really nail down the internal composition of all of the Galilean moons, the 4 largest moons of Jupiter, and to look for organic molecules on Europa. There's also NASA's Europa Clipper, which plans to launch in 2024. And the Clipper has similar goals to JUICE, but it's specifically focused on Europa and looking for good landing sites for a future Europa lander. Okay, so I've talked a lot about Jupiter, and as you can see, Jupiter is going to be getting a lot of attention in the next upcoming decades. But Saturn also has a ton of internally heated moons, and there's 2 main ones that I want to talk about today. And those are Enceladus and Titan. Let's start with Enceladus. Enceladus is one of the many moons of Saturn. It's quite small. It's about 1/10 of the size of Titan. Titan is Enceladus's largest moon. For some size reference here, so we've got Enceladus, Europa, this is another moon of Jupiter, and then Earth. So Enceladus is really, really small. If you put it on top of Earth, it's about the size of the UK. And it's so small that we can't really see it using telescopes on Earth. We can, but we can't really get much information about it. And so the first interest in Enceladus really picked up when the Voyager missions flew past it in the early 1980s. So this was an image that was taken by Voyager 1 of Saturn. And then that tiny little dot that you probably can't even see is Enceladus. And then this here is a zoom in and an enhancement of that dot. And so what was interesting about this image of Enceladus is that its surface was extremely reflective or bright. And that implies that there's some sort of geological activity going on Enceladus. So think ice volcanoes, but at the time, we didn't know what could possibly be causing such a small, cold body to have geological activity. But since Enceladus is so small and so far away, we basically just got that image, and then we had to wait until the next mission to Saturn. And that next mission didn't come until the mid-2000s when the Cassini-Huygens mission reached the Saturnian system. And this is a true color image of Enceladus that was taken by Cassini. Cassini flew by Enceladus several times during its 8-year mission. And not only did Cassini confirm that Enceladus has this really bright young surface, but it also discovered evidence that Enceladus is not completely frozen solid, but rather has an internal structure much like Europa's, with a hot core, an icy crust, and a global subsurface ocean of liquid water. And much like Europa, Enceladus also has a lot of cracks on its surface where plumes from the subsurface ocean erupt to its surface. And this is actually an image of those plumes erupting on Enceladus that was taken by Cassini. So Enceladus and Europa are very similar, but there are some factors that make Enceladus a little bit more favorable than Europa for life, and particularly life detection, including the fact that Enceladus's plume is much stronger and erupts much more material. So we can get better indirect sampling of the subsurface ocean on Enceladus than we can on Europa. It's much easier to just fly through the plume of Enceladus and pick up material than it is for Europa. But the trade-off with Enceladus is that Saturn is much further away than Jupiter. So Europa has really been kind of the focus of a lot of these upcoming ocean world targeted missions. It's just easier to get to Jupiter than it is to get to Saturn. But I think there's even more of a reason to go back to Saturn than just Enceladus. And so the last moon that I want to talk about today is Titan, which is Saturn's largest moon. That's this one here. So Titan's a weird one. It's slightly larger than our moon, but you can see it looks really different from many of the moons that we've looked at so far. And this is because what we're looking at here is not Titan's surface, it's Titan's atmosphere. So Titan has an extremely hazy atmosphere. It's difficult to see through the atmosphere because of how thick the haze is. But there actually was a successful Titan landing in 1997 from the European Space Agency. And to the right are just the images that it took on the way down. So at first you can see that it's in the haze, you can't really see much. And then it emerges from the haze and you see all these, fantastic geological features. You've got mountains, you've got ice, just an incredibly dynamic surface on Titan. And so Titan is also internally heated and likely has a subsurface liquid water ocean like the other moons that I've mentioned. But I think what's most compelling about Titan is what makes it different from the other moons. I'll note that this isn't a real image. This is an artistic rendering here. But what this shows is sort of an idea of what Titan's surface looks like. Titan's temperature is at a point that allows for a methane cycle. So methane is here, CH4, that's very similar to our water cycle on Earth. So on Earth, we have like water glaciers, we also have liquid water oceans, and we have water in our atmosphere. Titan's temperature is such that it has all three phases of methane on its surface. So Titan has methane ice glaciers, methane lakes, and methane in its atmosphere. And so I think Titan is really interesting because it expands our idea of how we define life. We've focused in so much on finding liquid water at all costs. But what about a moon where the temperature is such that methane effectively serves the same purposes as water? Could there be methane-based life on Titan? And what would methane-based life even look like? So as of now, NASA has no mission planned to go back to Saturn. But that is not discouraging to me. That is actually exciting because it means that we're in a phase where we can creatively think about what we want to look for and how we can go about finding it. So, what kind of instruments would we want to have on a spacecraft? What do we want to explore? What data do we need to further our scientific investigation to find life in our solar system? And even though these open-ended questions, as I said before, can be hard to think about scientifically, I really think that this is the beauty of the field of astrobiology. We get these opportunities to basically creatively redefine our search for life every time that we design a new mission. And so, while much of the time we have to narrow our focus, we have to carefully define our research and exploration questions, whenever we design new missions, we get to open up our minds and have all these out-of-the-box ideas and think about what we would really like to find. So that's everything that I have for you today. I want to say thank you to Tucker and to Wonderfest for putting this on, as well as Neil for giving a great talk earlier. I'm happy to take any questions now.
Wow, thank you, Erin. Maybe I will leap in here and take the opportunity to ask my question just because of we're going to be applauding both of you and at the end today, but let me ask a question, please, Erin. We've been hearing about very recent ongoing missions to Mars, one from NASA approaching Mars, one from the United Arab Emirates, and one from China. Do nations collaborate, if not in the actual construction and launch of their spacecraft, do they collaborate on avoiding duplication of research so that one craft can focus on one science and another a different science?
I think there are some groups that do collaborate quite well, but I think in general, there is, as you can see from JUICE and the Europa Clipper, which are launching at a very similar time, and they're both going to look at Europa. One's from NASA, one's from the European Space Agency. There often ends up being a lot of overlap. And that's not a bad thing. Different instruments, like nothing ends up being identical, really. And certainly with how much money it takes to build something and send it into space, you're not going to do it just to duplicate somebody else's results or try to get more precise measurements of the same thing. So a lot of times we have similar targets, and occasionally there will be some kind of overlap in working on projects collectively, or maybe one space agency builds an instrument that goes on another spacecraft from another agency. But I would say in general, it's really more that we end up having projects that are all looking at the same thing and sort of creating this like holistic picture and adding more data to the picture. I think actually that's what Cassini did really well. Cassini was a mission that just really, they made their data very like open access. They really wanted to get collaborators from all over the world analyzing their data. And so I think Cassini is an example. Cassini ended in 2018, and that was just looking at Saturn. I think Cassini is a great example of how we're starting to collaborate more, especially in terms of analyzing the data and working together on coming up with what the spacecraft has actually found.
Cool. Yeah, thank you, Erin. Okay, let's look at some of the chat room questions. Nick Canas asks about the possibility of methane-producing microbes on Mars.
Yeah.
Please, do you want to go ahead? You want to take that on?
So this is a whole controversial topic. There was a paper, I don't remember how long ago, a little while ago now, that basically posited that they had detected huge amounts of methane on Mars, and that the amount of methane that they had detected could only be explained biologically. And this paper basically caused a huge rift in the astrobiology community of people that said no way, and people that said yes, we've done it, we found life on Mars. And so since that initial paper, there has been no follow-up observations of the amount of methane that first paper recorded. So, there's a lot of people that think maybe that was an anomaly, maybe there was something wrong with the data. I think the possibility for methane producing microbes on Mars is it's not zero, certainly. I think there are pathways for life to exist on Mars. I think the struggle with Mars at this point is that, we've done a lot of looking, and at this point, how do you identify microbes or fossils or something like that with a rover? That's something that you generally would want to look at under a microscope and see that something's like swimming around there. It's really difficult to do with a rover. So I think it's definitely possible, and there's definitely a lot of talk about it in the Mars astrobiology community. But I think the evidence is pretty contested at this point.
Thanks, Erin. Evidently the Wonderfest bouncer has not been doing a good job, because somebody snuck in here to ask a tough question. Dan Wertheimer is a Wonderfest Sagan Prize winner. He's also the chief technologist of the Berkeley SETI program, Search for Extraterrestrial Intelligence. Dan snuck in here and asks, has anybody done a Miller-Urey-like experiment with methane and Titan-like temperatures? And if so, what happened?
I'm actually not sure about this one. I would think yes, because this is the origin of life is really like the, question mark black box in the whole equation that we still have really not filled out. Like, we haven't figured out how we go from the primordial soup, sort of like early Earth, pre-life conditions, to primitive life. And so there's a lot of like laboratory experiments that look on this for Earth conditions. So I imagine it would be similar for Titan and methane, because, obviously that's sort of that's the contingent point for Titan astrobiology, right? Is what's the pathway for methane-based life to evolve? So I don't know personally of experiments, but I think that would be, the case you would need to make really to justify life on Titan in a serious way.
I'm glad the bouncer didn't perform her duty. Rewa Bush asks, how common are these subsurface oceans in our solar system?
So confirmed, there's basically moons of Jupiter, moons of Saturn, not every single one, but basically all that have water ice. And we don't really understand why some have water and some don't. So that's sort of a mystery at this point. But, I mentioned a couple in this talk, but there's several others, moons of Jupiter and Saturn that we know just because we've had missions to Jupiter and Saturn in recent years. So we have good measurements. We think that there are many more subsurface oceans, not all necessarily being water. There's actually quite a debate about Pluto right now, whether Pluto has a subsurface global ocean. So I know that's something that New Horizons was looking at and that, people have really kind of debated. But we think that it's actually a relatively common phenomenon. I mean, if you think about the Earth, we have liquid layers in the internal, structure of the Earth. So if you have water or any other kind of ice like that, it's not so unrealistic to think that there could be liquid layers underlying icy surfaces that are icy just because, the body is really far out in the solar system, so it's not getting a lot of heat from the sun. So we think that they actually can be relatively common, though we don't have a ton of, 100% confirmed targets.
Great. Jim Lilienthal asks a related question. Do we know whether the moons of Jupiter and Saturn have had their current conditions for a very long time, say even billions of years, the time it would take, or the time it evidently took on Earth for even simple life forms to evolve?
So we think that, and this is, again, highly contested at this point, or we're still kind of filling in the blanks, but we think that at least the Galilean moons, so the 4 largest moons of Jupiter, formed relatively early on. And we think that they formed like inward out. So they didn't all form at one time. It's more like one formed and then another formed and moved out, another formed. So they're not all exactly the same formation timescale, but we think generally it was relatively early on and that this was kind of a process that occurred when Jupiter was forming itself. So that would mean billions of years. The question then is, what's the internal heating timescale? Has the internal heating always been there? And how long? And, you can do certain calculations with, we know right now how much plume outgassing there is on Enceladus, for example. So what if we back calculate that, how much mass has Enceladus lost over the last couple billion years if it's been outgassing at this rate, which would mean that it maybe has about the internal heating rate that it has right now. So there's a lot of modeling people that are looking at this. I just think at this point, all of these, the formation of the outer solar system in general is really a murky area. But certainly that's a very important factor in considering whether life could have even evolved on these bodies. Although there's a lot of people that like the idea of panspermia, that life on Earth could have been taken in a meteorite or something like that out to the outer solar system and infected basically some of these bodies, and that could also have happened. So there's plenty of people that model that as well. But yeah, it's definitely an open question.
Thanks, Erin. Lyle asks, first he comments, that was an outstanding articulate talk. Thank you. And he asks, will we be bringing back samples from Mars so we can examine them for possible fossil records?
I don't know of anything that's planning a return from Mars, but I could be wrong on that. I think there's a lot of people like Elon Musk that would love to have a lot of back and forth between us and Mars, but at this point, I don't think that there's plans to return stuff from Mars, but I could be wrong on that, actually. But yeah, I mean, that's basically what I think you'd have to do is I think you would have to actually get physical samples and look at them in the lab to really confirm something like a bacteria fossil or even bacteria itself.
Okay. Eric, single name celebrity perhaps, asks, are there any belter worlds with water? Do you think he means asteroid belt, or is the word better what he intended?
Belter worlds. I'm trying to think if there are any asteroid worlds with water. Certainly water ice. I think we found asteroids and comets definitely with water ice. I think in terms of if the interpretation is better, then I think, my personal favorite is Enceladus. That's just that's my bias. I really like Enceladus. I think it's very cute, and I think it's the most promising. But yeah, certainly no better worlds for surface water, at least in our solar system. I think Earth still wins that one.
Great. Stuart Newsom asks, would you have an idea on what will happen to us, to humans, as we eventually colonize far-flung planets? Would we become isolated populations like Darwin's tortoises and finches? So would we become distinct species?
Oh, this is a loaded question. I'm not 100% sold on the idea that colonization of other planets is a given. I think actually, what I said in the beginning of this talk is that our search for life in space is based on all these assumptions about what we think is like human nature or universal truths or whatever. And I think colonization is one of them, that we kind of think, okay, well, it's the natural order for us to move out into the solar system and colonize Mars and colonize the moon and, go to all these places. And I'm not sold on that entirely. And I know that that's not what a lot of space people want to hear, because a lot of space people are very into the idea of going all over the place. But, I think we've evolved very specifically for Earth. And while I think that, we'll continue to do lots of scientific exploration and potentially some, kind of human exploration on Mars or the moon, I don't really see us, going out and colonizing planets in the galaxy or in our solar system in that way. But that's more of a personal opinion. But I think, these are the kind of philosophical questions that, really end up coming up in astrobiology, and it's part of why I love this field. But yeah, I appreciate your question. I love thinking about this topic, and it's really very multifaceted.
Yeah. Dan Wertheimer, the SETI expert, has commented that there are, when a big rock hits Mars, small pieces of Mars go flying around the solar system and occasionally hit Earth. You can find them in Antarctica. And in fact, Dan says they have some of those Martian fragments, Martian meteorites, in their lab at the Space Science Lab. Very cool, at UC Berkeley.
Right, Martian meteorites. There definitely are rocks from Mars. I think I was more thinking along the lines of, okay, what if you found a really promising astrobiological site and you wanted to specifically look at that rock? I don't think that we have a mission planned to do specific returns like that. But that is a good point, that we do have Martian rocks on Earth now.
Great. Sari offers thanks to you, to Neil, and even to me, and I get to come in here with some thanks. I want to say that I appreciate you, the Wondernauts, even if you don't like that title, for being here tonight. Thank you, Zoom audience. Thanks also to those of you who have donated and are perhaps even donated to and are patrons of Wonderfest. Thanks for your $1 or $2 or more.